All right, so yesterday we primarily talked about finding unique sets of protons and carbons, and the big takeaway from yesterday's lecture was protons are chemically equivalent if they're in the same type of environment. So in our first example, we said A and B are equivalent because they're in the same environment. Therefore, you only have one signal for that set of protons. If we look down at more complicated ones, like this one, we said that A and B are actually different, but they're unique sets, right? So we've got 4 protons making up the set for HA and 6 protons making up the set for HB, and we should see 2 unique signals for that. We talked about some other ones like ethanol, and then later on we even went so far as talking about diastereotopic protons. Those are ones that look like they're kind of in the same chemical environment, but they're not. And the easiest way to do that is to swap one or the other for a deuterium atom and compare those 2 compounds. If they're diastereomers, that means they're going to be unique sets of protons and they're diastereotopic. All right, so today we're going to take this a step further and talk more about the signals themselves. And this has a unique term. It's called multiplicity, and it talks about what shape the signal should be. So will it be one sharp peak or will it be a jagged set of peaks? We don't really know until we start investigating this in more detail. And this gets into a lot of physics, so I'm going to try to dumb it down to the level we need to know for OChem. If you go on and take physical chemistry, you'll talk about this in a lot more detail. And the most important thing to remember is that nuclei have spin, right? We talked about that yesterday. And the spin can either be spin up or spin down in that magnetic field. So let's write that. Can be spin up or down, and they can have spin-spin coupling with neighboring nuclei. And I'll describe what that means. The easiest way to describe this is that nuclei that have neighbors next to them actually feel those neighbors, and those neighbors will impact the signal shape. So let's take a look at a really simple example. We're going to just make this super basic. So let's look at how HA affects HB. Oop. So we're going to look at how neighboring HBs affect HA, and I'll do HA as red. Okay, so we're primarily looking at the signal for HA, but we know that there's some HBs nearby that are going to mess up its signal to some extent. Okay, so let's take a look at some various examples. And so in this simple example, I've got a carbon-carbon bond. I've got HA over here on the right-hand side. And we're going to have some bonds coming off here. I'm just going to leave those blank right now, but we know that these are not hydrogen, so I'm just going to put an R group right here as a placeholder. Does that make sense? So the R's are not hydrogen. So just consider the R groups placeholders. In fact, I'm just not even going to draw them. How about that? Just to avoid confusion. All right, so this HA has one neighbor, HB. All right, if we think about HB, because it has nuclear spin, can exist in 2 different states, right? It could either be spin up or it could be spin down. So let's write this over here. So possible HB spin states. And we just said it could either be spin up, so I'll put HB kind of in a box here, or it could be spin down. All right, so if we think about this, it's equal probability of being either spin up or spin down, so it's a 1-to-1 ratio in terms of the probabilities. So if we think about the peak for HA, it's actually going to interact with each of these spin states slightly differently. And so what you'll end up with is one peak split into 2 smaller peaks. It's a little hard to imagine, but I'll draw what it looks like. So imagine a big, tall peak now is split into what's called a doublet peak. So people will call these doublets, or they just abbreviate it as D for a doublet. Does that make sense? Simple situation. What do you think happens if HA has no neighboring protons? What will the peak look like? It'll just be a single peak, right? It has nothing nearby to split it into smaller peaks. All right, so let's look at a harder example now. So this time we're going to have two HBs. So I'll draw these HBs right here. I've got HA right here. All right, now we have to think about the set for HB, right? There's two protons in that set. They both could be spin up, right? That's one possibility. So in this set, I'll put them in a box. One probability is they're both spin up. What's another probability? Both spin down. That's another probability. Or we could have, let's say, one of them up, the other one down. Or alternatively, one down, one up. So in terms of, I'm actually going to slide this down. In terms of the statistics for this, this is going to be a 1 to 3 to 1 ratio, right? In terms of the possible spin, or sorry, 1 to 2 to 1 ratio for the possible spin states. All right, so now when we look at this, it'll actually have a peak that's split into 3 different mini peaks. However, the middlemost peak will be slightly taller than the outer ones because it's a 1 to 2 to 1 ratio for those peaks. So when we look at this peak, it'll look kind of like this, almost like a mini trident. And this is a triplet. And again, people like to just abbreviate things, so they just call that a T. Does that make sense?
So you paired the two middle ones together?
Yeah, exactly. If we think about these middle ones, right, the overall outcome of those sets are identical. However, there's 2 times more likely chance that you'll run into one of those than a spin up only or a spin down only, if that makes sense. Okay, so let's try some more challenging ones. Let's do HA with 3 of them, and we may call it good after that just because I don't want to do all of the crazy ones. So we'll call this HA, and then all of these will be HB. All right, same sort of thing. We could say, well, all of the HBs could be spin up in that set. That's one probability. Or we could say all of them could be spin down. That's another probability, but the probability of hitting all spin up or all spin down is relatively low, right? Alternatively, we could have 2 up and 1 down. However, this could occur in any number of configurations, right? So I'm actually going to slide this down too. Sorry. Come on. Help me out. Doesn't like it when I'm attached to a projector. There we go. All right. Sorry about that. So they could be 2 spin up, 1 spin down, but this could occur with this configuration, right? The net for this one is still 2 spin up, 2 spin down, but it's slightly different. Or it could be spin down, spin up, up. All of these have a net of 2 spin up, 1 spin down, right? All right? Those are the 3 possible combos. Alternatively, we could have 2 spin down, 1 spin up. Or we could have down, up, down. Or we could have up, down, down. A little bit weird to think about. But those ones are far more likely to run into a situation where you've got 2 up and 1 down, or 2 down and 1 up. And if we think about the ratios here, it's a 1 to 3 to 3 to 1 ratio. So if we think about this peak, it's going to be split into 4 small peaks, right? The 2 inner peaks, though, will be about the same height because they'll be the same probability, and then the outer peak will be about the same height. So again, this looks almost like a fork with the outer prongs 1/3 the height of the inner prongs. Does that make sense? This is called a quartet. And again, people just abbreviate this Q so that they don't have to write out quartet. Does that make sense? What do you think happens if we've got 4 HBs? What signal shape should we see? Without even doing the spin up, spin down thing. Yeah, we don't even need to know the ratios, right? If we notice we went from a doublet to a triplet to a quartet, what if we have 4 HBs? We'd have 5 peaks, a quintet, right? So you can keep on doing that. The really simple trick you can do to predict the splitting pattern is take the number of neighboring protons and add 1 to it. So we call that our n+1 rule in order to predict splitting. So in this case that we just went over here, we had 3 HBs. Add 1 to that, we get a quartet. So it's pretty easy to predict. So let's make some notes here. So use n+1 rule for predicting splitting. And we said, for example, 4 HBs give HA a quintet. Make sense? All right, there's some other nitty-gritty details we do have to go over. One is that HA can only feel protons that are 2 or 3 bonds away. And I'm going to put feel in quotes here because we know that they can't actually feel them in the true sense. And what I mean by this is, let's go back up and look at our example, right? If we look at HA and its relationship to HB, there are 3 bonds in between HA and HB. That means that this is allowable via NMR. However, if they're 4 bonds away from one another, you don't see any splitting due to that. So you can only see protons that are 2 or 3 bonds away. Yep? So up here, for this example, we had 3 HBs. Yeah, so I was taking this one further. It was one we didn't do. Where if, for example, we potentially have 4 HBs nearby, then we would say, all right, HA is actually going to show up as a quintet due to that n+1 rule. Yeah, the one above we had 3 HBs. This one I was saying 4 HBs, if that makes sense. Okay, so that's one important thing. You can only look at neighbor protons that are 2 or 3 bonds away. And then last but not least, HA can't be split by other HAs. Oop. That is to say, equivalent protons don't split one another. Does that make sense? So when you're looking at splitting, you only want to look at protons nearby that aren't equivalent to the proton you're investigating. All right, last but not least, we've got one more rule I want to slide in. HA cannot feel protons if you must go through a non-carbon atom. to find a neighbor. And I'll show you guys an example of this in a second, but there's a lot of rules. It makes a lot more sense when you actually look at the spectra though. So let's take an example, and for this example, we're going to look at ethanol. It was one we looked at yesterday. So ethanol, we said we've got 2 carbons with an alcohol. The central carbon, in fact, let me draw out all of our bonds, has 2 hydrogens. The alcohol has 1, and then we've got a methyl group on the end. All right, I really am a fan of these charts where we do HX, and then we'll do intensity over here. And now we've got a new column for multiplicity, meaning what does the peak look like. All right, so we know we've got HAs down here. So I'm going to go in and fill that out. I'll say HA. We know we've got HB right here. So I'll say HB. And then over here I've got HC. So I'm going to put that in last. So we've got 3 unique types of protons on here. Does that make sense? Review from yesterday. All right, now we need to do that integration, meaning what's the area underneath the peak going to be for the ratios, right? So HA, what should that be? 3, right? So it should be roughly a 3 to 2 to 1 ratio, right? Because we've got 3 times as many HAs as HC, right? It could be 300, 200, and 100. Doesn't matter. All we care about is the ratio. All right, now the tricky part, multiplicity. So let's think about HA, right? How many neighboring protons does HA have that aren't equivalent? 2, right? If we think about it, to go from HA to HB, we go 1 bond, 2 bond, 3 bonds. So HBs are 3 bonds away, right? All right, we've got 2 HB protons. So what will the signal be for HA? Will it be a singlet, doublet, triplet? What do you guys think? Be a triplet, right? We've got 2 of them. We add 1 to that. That means it should show up as a triplet. So for this one, I'll just write triplet. I'm going to erase this so we don't confuse ourselves with the colors. All right, and now we want to focus on HB, right? So HB is a little bit trickier. We know that HAs are neighbors. They're 3 bonds away from the HB set. All right, what about HC though? It is 3 bonds away, but what's the problem? Yeah, we've got a non-carbon atom in our path when we're looking for 3 bond neighbors. So in this case, HC doesn't truly count as a neighbor because we can't go through that oxygen atom. All right, so when we're looking at HB, we'd say, all right, really it's only neighbors that we care about are the HA set. We've got 3 of them. So what should the splitting be for HB? Quartet, exactly. And then lonely old HC, how many neighbors does it have, technically? Has none, right? Because we can't go through non-carbon atoms to find neighbors. All right, so what should that show up as? 0 plus 1 means we get a singlet, right? So this would just be a singlet peak. All right, so let's take a look at the spectrum. I didn't want to give it away. But here's the spectrum for ethanol. If you remember, I told you guys you have this x-axis with typically 0 on the far right-hand side and up to 15 on the left-hand side, and that's in parts per million. And you can see quite clearly we've got 3 unique sets of peaks because we've got 3 different types of protons. All right, right here, what does that kind of look like? Looks like a quartet. So that must be the signal for HB. Make sense? All right, what about this one right here? What does that look like? Singlet. So that's got to be HC, right? We just predicted that. And then over here, that looks like a triplet to me. So that must be HA. And we know that simply by process of elimination too. Does that make sense? In addition to that, we could look at the relative area under these peaks, and we could say the entire peak area for HB is twice as big as the area under HC, and the entire peak area under HA is 3 times as big as the peak area under HC. You have to look at the entire area underneath all of the little peaks in one set. So for example, this triplet right here, you need to include the area under the left prong, the middle prong, and the right prong as the overall area for that peak. Does that make sense? That's the integration value that we were talking about yesterday. All right. These do get a little bit tricky, but the more you work with them, the easier they get. So do you guys want to try a new example? We can predict it and then even draw an anticipated structure. So predict number of unique proton symbols their integration and their multiplicity. All right, in the example I'll give you look like this. So we want to start out first determining the number of unique protons. Integration's pretty easy, right? And then multiplicity is the hard part. So I'll give you guys a minute to work on this, but check with your neighbor and see if you agree with one another. All right, so let's really quickly do the number of unique protons. If I look at this molecule, first thing I notice is we've got symmetry cutting it in half, right? So the left-hand side is the exact same as the right-hand side. Then what I would do is I'd say, hey, I've got some protons coming right there. We know that those protons must be the same on the right-hand side and the left-hand side, so I'll just draw all of them in. Say, all right, all of these red protons are identical. And it's important to remember, too, like I said yesterday, those methyl groups spin like helicopter blades, which is why all of those red protons are equivalent to each other in each methyl group set. Okay? If we think about the center right here, I also have one remaining proton there, so I'll label that in orange. So that's unique, right? We don't have any other protons in an isopropyl group like that. All right, what about right there? No hydrogens, right? So we would ignore that one. Then I would say, all right, what about this one? Yeah, on the left-hand side, we must have an equivalent one. The tricky thing is the proton underneath going to be equivalent? No, we don't have a horizontal plane of symmetry. So what we do is say, all right, this proton must be unique, so I'll label that as green. So I'll label this as 1, 2, 3, 4 unique sets. The first one we labeled was HA. I'll label this one HB in orange, and then we've got C and then D. Does that make sense so far? All right. Integration-wise, for the HA set in red, how many will make up that peak? 6. Hopefully we're good at counting. How about the orange one? 1. And then 2 and 2, right? So that part's actually, in my opinion, the easiest. The tricky part now becomes predicting the splitting pattern or the multiplicity, right? All right, so imagine that you're the red protons, right? How many neighboring protons do you have that are 2 or 3 bonds away that aren't another red proton? 1. So what should the splitting pattern be? A doublet, right? Not too bad, right? All right, what about HB? How many 3-bond neighbors does it have? 6, exactly. Why don't we count the blue one? It's more than 3 bonds away, right? To go from that orange proton to the blue proton, that's 4 bonds. We can't do that. We can only look at 3 bond neighbors, right? So if we look at that orange proton, we'd say, well, it has 6 red protons that are all 3 bond neighbors. So what do you think this peak will look like? A mess. So it'll have 7 prongs in it, right? 7 prongs is a septet. I'll call those prongs. That's not the scientific term, but you get the idea. All right. All right, HC. How many 3-bond neighbors does it have for the blue one? Only 1, right? We know it can't be split by anything that's 4 bonds away, so the orange proton doesn't count, and it can't be split by itself, so it can't go across the ring and be split by the other blue proton. Yep.
Yeah, the bond, what are you counting?
Yeah, that's a great question. So if we think about bond distance, right, we'd say, whoa, sorry. Let me redraw this. That's 1 bond. That would be a second bond, and that would be a third bond. So we can look at 3 bonds. However, for example, students get tempted to say, well, what about 1, 2, 3, 4? That's too many bonds. So we don't look at the orange proton because that's 4 bonds away, not 3 bonds away. So only look at 3 bond neighbors or 2 bond neighbors. 95% of the time you're looking for 3 bond neighbors. I'll show you an example with 2 bond later on. They just aren't as common. Does that make sense? Okay. All right, so we've got that. So knowing that the blue proton has a 3 bond neighbor that's the green proton, how many, or what should our multiplicity be? A doublet, exactly. And students oftentimes get confused and they say, well, each blue proton has 1 3 bond neighbor, so shouldn't we get a triplet out of this? Remember that we're only looking at 1/2 of the molecule. Both of those behave as their own unique set. So in this case, they only have 1 3 bond neighbor, and that means this will be a unique doublet. I'm going to erase this so we don't confuse people. Come on. Or maybe I'll do that later. Sorry, my laptop might be dying on me. I've been looking at getting a new one. All right, how about the green one? What should the splitting be? A doublet, right? All right, so let's try to predict, come on, what the spectrum will look like. And so I'll just draw an example one. And like I said, typically it'll go potentially up to 15, although peaks rarely show up at 15. All right, so protons coming off of an aromatic ring typically show up around 6 to 9 ppm. I'll give you guys a cheat sheet so that you guys can know where peaks show up. But we should have 2 doublets in that range, right? So what we can do is say, all right, 6 to 9 ppm, I'll have 1 doublet, and then maybe another doublet right next to it. Does that make sense? For each of those protons. It's really hard to tell which one is which, so I'll just say, all right, arbitrarily I'm going to label one as HC and then the other as HD. I'll give you guys a handout later on. I forgot to photocopy them today, but I'll post them on the website. And then you also get them on the exam too. However, aromatic protons always show up in that region for the most part. All right, and then if we think about the remaining protons, we're missing a septet and a doublet. The septet will probably show up closer to 2. And I'm not very good at drawing a septet, so I'm just going to draw this as what you call the mess. And we know that this must be HB. But if you go and zoom in on that peak, you should see 7 unique prongs in that peak. All right, and then HA, on the other hand, must be pretty big, right? So HA must be a really big doublet. Whoops. So I'll go ahead and fill in that really big doublet. And it'll look like that. And this should be HA. I'm not very good at drawing these to scale, but HA should be 6 times as large as HB. The area underneath the peak should be 6 times as big. Does that make sense? So we want to look at the integration of those as well. All right, let's take a look at another example. Yep.
What is HC and D the double of HB? The size?
Yes, so you're talking about HC and HD. HC and HD should technically be twice as large as HB. I'm just really crummy at drawing a septet. So if you actually look at your NMR spectrum and you use the computer to measure the area underneath each set of peaks, the peak for HC should be twice as big as the peak for HB. Yep.
So for the last example that we did with the ethanol one, the actual, it was actual graph.
Yep.
So for the HB, like one of the peaks was higher than the other one. Is that like common or?
Yeah, so you're bringing up the peak height, right? So peak height is different than peak area, right?
Oh, okay.
So what we're looking at with integration is the area underneath the peak, not just simply how tall it is. How tall it is doesn't tell you the area. That's a really good distinguishing thing to remember. That peak height tells you nothing. All right. Let's try another one. This one we're not going to draw everything out for, but I'll just do this. This one's going to be a little bit harder, but just like before, we want to find the number of unique protons and then determine their relative integration and then determine their multiplicity. All right, quick show of hands. How many unique protons? You guys getting 6? No? So let's go through and check. This is a good point to check. All right, so this one I'll call HA, right? How about these ones? I'd say they're unique, but equivalent to one another. So I'd say HB. And then over here, I'd say, all right, we got HCs. 2 protons right there and there. All right, what about this proton right there? That is a unique proton, but are there any others like it? Yeah, on the other half of the aromatic ring. Because we know that this aromatic ring has a plane of symmetry, and this upper group can actually flop around in space. So, oops, sorry, these should be both HDs. So both HDs technically occupy that same chemical environment. All right, then down here we've got HE, and that must be equivalent to down here, which is HE. And then we also have all 3 of these protons, so I'll call these HF, HF, HF. So I've got A, B, C, D, E, and F. All right, integration for A. This is the easy part. 1. What about B? 2. C? 2. D? 2. E? 2. And F? 3. All right, so that's our ratio of peak areas. All right, multiplicity for A.
0. So sigma.
Is it? HBs are 3 bonds away, right? So both HBs are 3 bonds away, which means they will split. We've got 2 3-bond neighbors. 2 plus 1 means we must have a triplet. All right, what about HC? Yeah, HBs are 3-bond neighbors. We've got 2 of them. So it must also be a triplet, right? Or sorry, we're on HB. I was thinking HC. HB has how many 3-bond neighbors? 3, right? So this would be potentially a quartet. However, we'll come back and talk about this more. HB is actually going to look a little bit different than a quartet because HC, that one set of 3-bond neighbors, is different than HA, its other 3-bond neighbors. So this might not look like a very pretty quartet. And we'll talk about that next lecture period. All right, what about HC? That was the triplet one I skipped to. All right, so it has 2 3-bond neighbors. Add 1, we get a triplet. All right, what about HD? Has 1 3-bond neighbor, so this would be a doublet. All right, what about HE? A doublet. And what about HF? Singlet, it has no 3-bond neighbors. All right, so what I want you guys to do for your pod is ignore the drawing of the spectrum, just include the chart. What I mean by that is include this, label all of your protons, and then predict their integration and multiplicity. On Monday when we come back, we'll learn about chemical shift more, and I'll give you that cheat sheet and show you how to predict where it shows up on the spectrum. Does that make sense? All right. Good luck studying, and feel free to email me if you guys have any questions over the weekend.